Good morning, Astronomy 1010. Welcome to the second part of our lecture on planetary geology, where we look inside the hearts of terrestrial planets to find out what makes them tick. And then we try to figure out how what's happening on the inside of a terrestrial planet bubbles up to the surface to shape the cool geology of planets that we know and love so much, like our own Earth. I just noticed that these overhead lamps are on. Let me fix that. So, as a kind of preamble to what I'm going to do today, I want to show you guys a couple of slides. And I wish I had one for all the terrestrial planets, but I found 3 grayscale maps that show the surface topography of some of the terrestrial planets, and they're all the same. They're devoid of color. And it turns out to be a pretty cool exercise to see if you guys can guess which planet it is. Up to now, we've kind of talked in general about terrestrial planets. And once you know a little more about how internal heating and geology work, I'd like to actually go into the specifics of the planets. But let's just start here, function F5. There's no reason you should know what planetary surface this is, but this is one of the terrestrial planets. See if you can guess which one. You're looking at a complete topographical map in grayscale of one of the terrestrial planets.
Could that be Earth, since there's not a lot of crater impacts going on?
Ooh, now that's a sophisticated answer, Ian. I didn't know you knew about such things already. That's part of today's lesson, is that impact craters tell a story about how old a planetary surface is. I don't think it's Earth, Ian, because my next slide, okay, that failed. My next slide is going to be that one. What planet do you think that is, Ian?
Well, that's definitely Earth. You can literally see the continents.
Exactly. When you see Earth, you ain't confused about it. You recognize these land masses, correct? So this can't be Earth. What could it be? Your ideas are... Oh.
Could it be Mars?
No.
I was going to guess Venus.
Yeah. This is the surface of Venus. Believe it or not, of all the planets in our solar system, definitely of the terrestrials and maybe even of all the other planets, we have better images of the surface of Pluto than we do of Venus. Venus is a mystery to us. Now, how do I have such a topographical map? We've been able to map the surface of Venus despite not being able to see it that clearly by bouncing sensitive radio waves off the surface, measuring their reflectivity, and microscopic differences in the time lag allow us to recreate a model of the topography. Okay, here's one more.
That one's Mars. I feel like I recognize that.
Yeah, we're actually becoming quite familiar with the surface of Mars, not only because its atmosphere is thin and transparent, so we can see pictures of it on the internet that are taken with, say, the Hubble Space Telescope. We also have rovers that have landed on the surface. We have satellites that orbit Mars and continuously make high-resolution images. Mars is imprinted on the psyche of humankind in a way. No other planet holds so much historical fascination for us. Today, I'm hoping you're going to learn it's because it had a proto-Earth-like development. Our planet bears more similarities to Mars than it does to Venus, which is kind of funky to think about. Venus is our sister planet. Do you remember when I listed the radii of the planets? What was the radius of Venus compared to Earth?
It was only 350 kilometers less than Earth.
Yeah, and remember, it's 350 out of 6,000, right, Jenna? So I'm a guy who tends to think in percentages rather than subtractive differences. 350 out of 400 is a big difference. 350 out of 6,400 is 5%, right? Okay, just saying, you know. Okay, last time we learned, or today I suppose we'll learn, that how much of this cool stuff we see is in many ways connected to the amount of interior heat that a planet has. Remember, I made this distinction last time. It's an important one. Surface temperature is not the same as internal heat. They're separate issues, okay? Surface temperature affects the humans and the bunnies and the trees and the atmosphere. But the geological features that we see, they in a way kind of, most of them anyways, bubble up from underneath. That will be today's story. Let's start by doing some good remembering, because if you can't remember what we did last time, then it's kind of pointless to talk about today. How do planets gain internal heat in the first place? What makes a planet hot on the inside?
From accretion,
Yeah, and what does that term mean?
that is the heat of formation from gravitational potential energy. So basically that planets all start off hot.
Yeah, when you squish a bunch of gas and dust down to form a planet, it will be warm. I mean, hell, it shouldn't come as a surprise. When you release gravitational potential energy, that energy needs to go somewhere. If I take this ruler, I hold it above my head, approximately 2 meters, and I release this ruler, it makes a loud crash when it hits the ground. That potential energy must be released in some form. And here, in the case of the ruler, it takes the form of sound. But when you create a planet, it's like you're dropping 10 bazillion chunks of metal and rock all down on top of each other, not just vertically, but spherically from all directions. And that, of course, releases gravitational potential energy. There's no sound in space. That energy will go into the heating up of that metal and rock. Okay, the other two, Jenna. Did I spell that right? I think so.
Differentiation and radioactive decay.
So tell me a little bit about that.
Differentiation are basically kind of what you just described, when heavy metals sink and the light silicons rise.
Right. When we look at that picture, crust, mantle, core, we can see that Earth has kind of settled itself into a kind of, I'm looking for an analogy here. I had this ex-girlfriend that used to love to drink something very gross, in my opinion. It's called a pineapple upside down martini or something. It was just pineapple. Am I remembering this right? Upside down. Maybe it was, maybe cake would have been more, PG-13 here, or PG, shall we say. This is probably, but yeah. So this gross concoction, one of my ex-girlfriends used to think was the bee's knees. I don't know why anyone would do this to themselves, but I can't help but think about the analogy between the pineapple upside down martini and the differentiated layers of Earth's interior. The fact that this drink would separate itself into layers, pockets of sugar, okay? I don't know how the physics of the pineapple upside down martini works, but I suspect it's probably somewhat similar to the fact that these materials have different densities. The heavy things sink to the bottom, the light stuff sits on top. And Earth didn't start out that way. Remember that the protosolar nebula was homogeneous, it was well mixed. So these materials had to separate over time, and the rubbing generates internal heat. How about the last one?
Radioactive decay, which are unstable isotopes.
Okay. And here's where I want to pick up. In our lecture on the sun, you learned a teensy bit, I think. We talked just a little bit about fusion, did we not? Did we get to that? Because I remember doing a little bit on that.
We did.
I guess I will need my lecture on the sun today. I'm not talking about fusion. I'm talking about radioactivity due to fission. Let me call up the slide and you guys explain to me the difference. make me encouraged that you know the difference between fusion and fission. Shoot.
Fission is a splitting of a nuclei, usually when something smashes into it that separates it. And fusion is when small nuclei come together and they create a small amount of energy, but it leaves less, it's cleaner and leaves less waste than fission.
Right. One can often measure the radioactivity in their environment with a device such as this, a Geiger counter, okay? Maybe it's time for a little show and tell on radioactivity. This Geiger counter allows me to measure, okay, so maybe we could have just a quick kids break. I don't know if I totally have time for this today, but I'll make time for it. You've heard of Madame Curie, the woman who won the Nobel Prize in Physics in 1903 for her investigations into radioactivity. Oh, Kim, remind me what that dog's name again. I always hear it yapping in the background. What's that Poochie's name?
Luna.
Luna. That's right. Oh yeah, how astronomy appropriate, right? Luna's always a welcome addition to this class. Oh boy, I sure hope I didn't break this thing. Okay, sorry, I just had the wrong end. Okay, so I don't know if you've seen one of these like in a science fiction movie or something, but this is a Geiger counter. And Geiger counters are basically little particle detectors. They're designed to measure radioactivity of substances or even just the air in the room. When Madame Curie was studying radium and these other radioactive substances, by the way, it cost her life because they didn't exactly know what they were getting into. People were still trying to understand and figure out the electromagnetic spectrum. They knew that there was visible light, and they were starting to get a sense that there was infrared light, and I'm not sure if they knew about radio waves quite yet, but they were exploring different areas of the electromagnetic spectrum. And at first, when she left these photographic plates in the dark at night next to these radioactive substances, she discovered that there was some invisible form of light that was exposing these photographic films. And this led to a whole series of experiments to try to figure out what was going on. Eventually, she discovered what is called the 3 types of particle radiation, except it's not that simple or easy. Madame Curie discovered, let's call it the 3 types of what I would call particle radiation. It turned out that these weren't exactly electromagnetic waves, although some of them were. It's a bit messy here, okay? So there's alpha particles, beta particles, and gamma particles. Have any of you heard of this before, or do any of you know what they are from maybe a chemistry class or from a physics class?
I've heard of them, but I couldn't tell you.
Okay, so here's what they turned out to be. An alpha particle turned out to be the nucleus of a helium atom. Who knows what the nucleus of a helium atom is? Oh. Being the second most abundant element in the solar system, I thought y'all might know what a
Is
helium
that,
atom.
I think I might be mixing it up with hydrogen, but is that the 1 proton, 1 neutron?
That's deuterium. That's a form of hydrogen.
Ah, okay.
No? Wow.
2 of each?
This could easily be a test question.
Yeah.
What's a helium atom? That could easily be a test question. So remember at this time, the nucleus of a helium atom, its atomic number is 2 protons, and you need 2 neutrons to glue it together. The nucleus of a helium atom, in fact, since you all didn't know that, you better put note to self. The helium nucleus is so stable in nuclear physics that it's got its own designation. They call it alpha particles. Alpha particles are helium nuclei. The beta particle, that turned out to be a free electron. And in a weird twist, the gamma ray was technically a form of electromagnetic radiation, as you already know. It's super, super short wavelength, super, super high energy photons. The thing is, at the gamma ray edge of the electromagnetic spectrum, photons actually behave more like particles than they do like waves. The particle properties of photons become very evident at the short wavelength of the spectrum. In fact, gamma rays can not only scatter off of electrons, but under the right conditions, you can actually get two gamma rays to collide and turn into an electron and a positron, a wacky effect called pair creation. You can actually transform gamma rays into electrons under the right conditions. That's definitely a head scratcher from the point of view of physics, because this is electromagnetic energy, this is mass. Somehow the two are connected, but we still don't know how. Kind of cool. These are the three types of particle radiation Madame Curie discovered, and these Geiger counters detect it, right? So I can turn the audio on. Let's see if you guys can hear the clicks. Not too much. Oh, here we go. You can see that occasionally it gets a click, because even during the course of this lecture, high-speed alpha particles and free electrons probably fly through the air and create little nuclear explosions in my forehead, but the energy is so small that I don't really notice it. Now, of course, we have a couple of test substances here. Radioactivity, my friends, okay? It's all around us. Let's see, what do we got? We got some good stuff here. We got ourselves some strontium 90. Oh, sorry. Yeah, strontium 90. That's a radioactive substance. These are test samples. Cobalt 60. Ooh, and what about polonium 210? I think that's what they killed that Russian FSB agent with in England. Okay, so I can go up to these and I can calibrate my Geiger counter on these test samples. Let's see, how can I do this in a way where okay, here we go. All right, so let's put these aside. Let's start with strontium 90. I can't remember which one of these is the craziest, but listen to the clicks. A few extra clicks. All right. Strontium 90 wasn't too hot. Try polonium 210. Ooh. Notice the clicks come at random intervals because the alpha particles and the beta particles are just randomly breaking apart. I used to have a really cool animation for this, but I can't figure out how to make Flash work anymore. I think it's cobalt 60 that's real wacky. Ooh. You guys hear that? Probably should watch my hands before lunch. Now, I have another special radioactive treat for you guys today. And this is to remind you that radioactive decay, this is going to show up in our homework session today, is all around us. Wait for it. Now, I make no secret about it. I keep some strange company. And one of my friends in college, he was this chemist. We used to drink beer and watch Ingmar Bergman films together. He got me a birthday present once. He went out to the Tankerverde swap meet, which is like this crazy yard sale in the middle of the desert where you can get anything from chopped up deer hoofs to old pistols and things. And he brought me back a sample of carnotite. I want you guys to take a look at this here. Do you see? Let's get my Logitech. I want to be able to zoom in on this so you can just see how crazy. It's a type of sandstone rock that's rich in uranium. Okay. Usually people who discover that I have this in my house get a little upset with me. This tends to upset people. Okay. Now, hold on a second. Let's go to autofocus. Let's bring this in here. Okay. Can you guys see all that stuff? I don't want to touch it because if I eat this stuff, it's not going to be good. You can see the sandstone, but can you see all that crazy yellow stuff? That's uranium ore. That's that yellow dust. That's what they make yellow cake from. Shall we give it a whirl here? Did you hear that? Okay. My house guest just went, ooh. Okay, so first I was told, don't worry. If you put it in a plastic box, that should shield you from most of the alpha particles. So then, after my pregnant office mate discovered that I was keeping this in my desk drawer, she got very, very upset with me, and rightfully so. Okay, I kind of forgot that it was in there. I bought myself a lead box. Unfortunately, I didn't know there was a difference between lead box and lead line box. So this box has a thin foil of lead that is supposed to protect me from radiation. Well, it's probably helping a little, right? Anyways, I'm going to go put this over here in the corner. 1 second. I guess my point is, if you can dig up that sandstone from...
I just want to make a comment.
I want to hear it.
Did you watch the Chernobyl on HBO, the series? This is reminding me heavily of it.
I've been dying to. I hear it's awesome. I hear it's really good, right?
Yeah, it was good. It was sad, of course, very tragic, but just like it was tragic, but it was just interesting, like how little they knew about the radioactivity.
Radioactivity has strange and unpredictable effects, right? I think, did I read about this in a different article, or did I see a preview of it where they showed like spiders that were living in the radioactive site that adapted to those high levels of radiation, but it kind of altered their biology. Like, it's wild, right? You know, human beings and all other organisms on Earth have adapted to live with a small amount of background radiation. There's some molecule that travels up and down your strands of DNA, repairing code errors that naturally show up, not just from radioactivity, but from random chemical reactions. You get a little too much sulfur in your blood or something, you know. So human beings can live with a small amount of radiation, and probably organisms could adapt to live with higher amounts if they had no choice. But in general, it tends to not work so well. Today, we will do a sample problem where we discover that a planet, and I mean, just think about it. We're just drilling on the top surface of the crust, and we find small pockets of uranium and plutonium and all this other stuff. Could you imagine how much randomness is spread inside the interior of Earth? Small amounts of radioactivity built up over a massive sphere, they generate and keep a planet warm. In fact, we think now that the Earth is pretty well differentiated, the reason that we still have active volcanism today and other types of geology, radioactivity is what really keeps big planets like Earth and Venus warm, even billions of years after the formation of our solar system. Okay, that was supposed to be a review, but I got a little carried away. Let's talk about the way planets cool. There's a nice slide. Okay, so obviously planets cool down with time, okay? And let's get rid of this slideshow. Let's go back to the planetary geology slideshow, which I think is this one. And remember that one of the ways we can tell how much interior heat a planet has is by looking at the depth of the lithosphere. Okay, Remind the class, anyone who remembers, what's the lithosphere all about?
The lithosphere is hard, brittle, frozen outer layer of a planet.
Right. And in the slideshow that I'm showing you, the lithosphere is superimposed onto layering by density, crust, mantle, core. The lithosphere is shown as a dotted black line. And the point of this cartoon picture is that the lithospheres of Venus and Earth are comparatively quite thin. Only the outermost layer of the planet is frozen. But planets like Mars, Mercury, and the Moon, their lithospheres extend deep into the interiors of the planets. And these planets have lost their interior heat and are frozen solid. What makes a planet cool? Well, your book tries to portray it as convection, conduction, radiation. And those heat transfer processes are all happening on a planet. But I think of a planet losing its heat to space only in one form. You can't conduct heat into a vacuum, nor can you have big bubbles of convection going into a vacuum, because a vacuum is nothing. The only way you can transfer heat into the vacuum of space is through radiation. Planets are hot potatoes, and they glow and shine away their light. Now, convection does buoy energy up through the warm rock. Remember in particular that layer called the asthenosphere underneath the lithosphere has warm bubbles of convective rock rising and sinking. The crust, or the lithosphere more properly, is solid. And the only way to transfer energy across a frozen solid like that is through conduction, just atom to atom jiggling. You can't have bubbles of rock rising and falling in granite mountains, right? So convection takes energy throughout the interior of the planet up towards the lithosphere. Conduction heats up the frying pan that is the surfaces of the planets through conduction. And then once you get to the surface, the planets shine away through radiation. Let's examine that with our calculators and do a quick exercise on it. Rather than portray it the way the book does, I'm going to take the note something like this. Planets are black bodies. And you guys know what that term means now, I believe. They cool by shining light, their internal light, into space. Let's imagine a planet like Earth. Earth has an average global temperature, I believe, of roughly 15 degrees Celsius. Let's convert that in our minds to Kelvin. It's 273 difference, correct? Because negative 273 is absolute zero. So 273, 283, 288 Kelvin. Let's ask ourselves the good old-fashioned questions that we've asked before. Question 1, how much light does Earth give off? And that really is a question of luminosity. We'll say per meter squared. How much light does Earth shine per meter squared? And question 2 will be, what type of radiation is it? What is the lambda max, the peak wavelength of emission? These are easily questions I might ask you to do on a final exam. Who knows how to do it? Really? Jenna?
Is it using the Stephen Boltzmann law and the Wien's law?
Yep, it's Stefan Boltzmann and Wien's law or Wien's law. So let's just do a little cheat sheet. So this one is brightness is sigma t to the fourth. That's the Stefan Boltzmann law. And this one is lambda max is 3 million Kelvin divided by the temperature. There are two simple formulas that can really help you figure out a lot of cool stuff. Unfortunately, I kind of took up too much space here, so let's erase this note, and let's do answer 1 here. The brightness is sigma times t to the 4th. The Stefan-Boltzmann constant is always the same, 6 times 10 to the negative 8 watts per meter squared per Kelvin to the 4th, times, open parentheses, 288 Kelvin, 4th power thereof. Why don't you guys plug that in for me? It's saying my internet connection is unstable, so apologies if I start to glitch out on you. Could you guys punch that up for me? I'm going too slow today. It's that melatonin. Yeah, Jenna.
I got 413.
So let's call it 410 because I suspect that 3 is not entirely reasonable.
Yeah, it was 412 point something.
Yeah. What are the units then,
Okay.
Jenna?
Is it mass meters squared?
Well, meters squared will be on the bottom, but that's not the same as meters squared on the top. And there's more to it than just that, right? Meters squared is an area. This is a quantity of radiation.
Oh yeah. So it'd be watts per meter squared.
That's right. So every square meter of the ground is radiating about 410 watts into space. And that's just because hot rocks glow. Warm rock glows. And Earth is warm rock at the surface. Warmish, anyways. Okay, what about answer number 2? Let's try Wien's law. Lambda max is equal to basically 3 million nanometer kelvins divided by 288 Kelvin. That should take you 0.5 seconds to do.
I got 1040 over, 1040 nanometers. No? Okay, maybe I put something wrong.
Count better.
I got 10,400 nanometers.
Yeah.
I see. I accidentally moved the.
Okay, watch out for that, okay? In what regime of the electromagnetic spectrum is that?
Radio waves?
No. You don't get to radio waves until you get to about a millimeter or so. You know what I really want to ask you guys, but I know you're not going to know the answer. How many microns is that? A nanometer is a billionth of a meter. A micrometer is a millionth of a meter.
What was the question? Is it in infrared?
That's right. This wavelength is 10.4 microns. It's customary to measure wavelengths in the infrared in microns. That symbol mu means micrometer. It's a standard metric prefix, micrometer. And this is clearly in the infrared. If you think about it, this isn't too different than the temperature of your body. Planets, just like humans, shine infrared light into the dark, and that's how they cool over time. Every square meter of Earth's surface is glowing with the ferocity of an overhead projector lamp in the infrared, shining that light into space. And this is how they cool down over time. Hello there, Zachary.
Hey,
This kind of gets me thinking. Seeing as it's watts per meter squared, should bigger planets shine more light into space, or should smaller planets shine light into space?
It doesn't matter.
Well, they all shine light into space, but which is more effective? Which gives off more light?
The bigger planet, because it has more surface area, it has more
Exactly.
luminosity.
This leads to a bit of a conundrum. A bigger planet will hold more heat, but a bigger planet also has more surface area to shine into space. To analyze this problem, it's customary in planetary science to consider what the book calls the surface area to volume ratio. I don't like the surface area to volume ratio because the formula ends up kind of confusing for intro students. We're going to do a variation on it, an upside down variation called volume to surface area ratio. Can I erase this? I need to get some board space here. Okay, this is coming up in our homeworks today, so I figured I'd pregame it a bit with you. It's a concept, it's not complicated. It makes good sense. Consider something called the volume to surface area ratio of a planet, okay? The volume, so we know that we're dealing with a sphere. Most of our planets are spherical. Actually, all planets are spherical. Radius r. The volume of a sphere is 4/3 pi r cubed. Spheres also have surface area. And in some long forgotten geometry class, one is taught that the surface area of a sphere is 4 pi r squared. Let us also consider that the volume is sort of proportional to the amount of internal heat that a planet has. More volume, more accretion, more differentiation, more radioactive isotopes. The surface area, on the other hand, is proportional to the cooling rate of a planet. Let's say the cooling rate. Therefore, if I take the volume to surface area ratio, I'm sort of taking the internal heat holding capacity of a planet, and I'm dividing it by the rate at which it's cooling. And the greater the volume to surface area ratio, that just basically means it's the amount of internal heat that it will hold, because the higher this ratio is, the more heat holding you get over cooling rate. Let's now divide 4/3 pi r cubed over 4 pi r squared. What's that reduced to? My algebra loving friends? Cancel out common terms.
Is it 4/3 r over 4?
What's 4?
Oh, does that become 1/4 if I did that right?
No. The 4's cancel out, right?
Okay, yeah, that was
Because, guys, 4/3 divided by 4, top of the top, top of the bottom, that becomes 1/3, right? So what's my final answer?
3r?
Not 3.
1/3.
1/3 are. The 3 is in the bottom, Jenna. The bottom of the top is the bottom, right? What does this tell me? The volume to surface area ratio grows as the radius of a planet. Or in other words, as the radius of a planet gets bigger and bigger and bigger, it has pound for pound more heat holding capacity than it does cooling rate. In other words, we've written this before, but we'll write it again. Bigger planets stay hotter longer. Key concept in planetary science. In fact, anyone who's ever baked some turkeys and baked potatoes in their ovens probably has an eternal idea about this. If you cooked a turkey and a baked potato at the same time for an hour or 2 hours or whatever in the oven, and you took them both out of the oven to cool on the windowsill, which would you expect to cool faster, the turkey or the baked potato?
The potato.
Sorry, Ian?
The potato.
Yeah, it's got a smaller volume to surface area ratio. It will radiate and convect its heat out faster than the turkey, which might stay hot for hours. This, of course, explains why, if I dab a few slides back here, this is why the lithospheres of Earth and Venus are so shallow, but Mars, Mercury, and the Moon have such deep lithospheres. These planets have shined themselves to death and have frozen themselves solid. This, of course, means there's going to be less cool active geology. And active geology is connected to a whole bunch of things. Okay, so at this point, you've learned that planets that hold more internal heat are bigger planets, and they will be more geologically active. But what form will that geology take? How does that heat bubble and leak its way out to the surface? It's time for a big concept in this week's lecture: the 4 geological processes. Geology is a complex discipline full of all sorts of nuances. We aren't going to have time for all of those nuances. You'll have to see one of my colleagues and take one of their interesting geology courses. We're going to look at it from a broad strokes planetary science perspective, just the sort of big picture. And if you do this, most geology that you find on the surface of Earth or the surfaces of other planets kind of boils itself down to one of 4 categories: impact cratering, volcanism, plate tectonics, and erosion. And the amount of internal heat that a planet has will determine at least these 3. This one is kind of a default. Let's take some notes on this. This is a really important thing, and a lot of questions are going to depend upon this. In fact, I should have gotten to this a lot sooner today, but I'm going slow, okay? Forgive me. Aristotle famously had a sculptor analogy. I like to have a sculptor analogy as well. I think of the 4 geological processes as the sort of sculptors that shape the surface of a planet. Ultimately, this is what makes one planet different from another. They are impact cratering, volcanism, plate tectonics. Now listen, we're going to see tectonic features on many of the planets, but a fully robust form of plate tectonics, I want you to start off by thinking about this. A fully robust set of plate tectonics is more or less unique to Earth. I'm going to be saying some things that are a little bit contradictory from time to time. I want you to think that plate tectonics are unique to Earth, but then I'm going to tell you that there's tectonic features in all the different planets, okay? Especially what we're going to see them when we look at the surface of Mars. And last is erosion. With my remaining half an hour or so, I'd like to just basically say a few words about each of these, enough so that you can get the idea of when we look at the surface of a planet, which of these things are we seeing? For instance, remember that picture I showed you where we had to guess which planet we were looking at? Let's see if I can find that again. Ian, when you looked at this picture of Earth, what did you say? How did you know that you were looking at Earth?
Well, this one in particular, I was saying because you can see the outlines of the continents.
Right. And if you had to peg that to one of the 4 geological processes, which would it be?
Tectonics.
Absolutely. Earth's robust set of plate tectonics is manifest right on the surface by seeing those continents, which are shaped and formed by the scraping of tectonic plates against each other. You can literally see Earth's robust plate tectonics in the continental landmasses. Compare that to Venus. What does this picture suggest about Venus and its geology?
There's very little, if any, plate tectonics. It's
Right.
mostly
Isn't
uniform.
that strange? It's a planet just as big as Earth, with just as thin a lithosphere in theory, and yet no plate tectonics on Venus. That's a mystery that I don't want to solve for you just yet. I want to leave a few things unspoken. We'll get to it eventually. What dominant form of geology, what kind of dominant forms of geology do we see on the surface of Mars here at a quick glance?
Impact cratering, for sure.
That's the first thing you notice is, holy cow, relative to Earth and Venus, there is a lot more impact cratering. That means something. But I also see stuff like this.
Volcanoes.
Right. And what about the so-called Valles Marineris?
Erosion, maybe?
This one turns out to be pretty strange. So this is kind of like Mars's version of the Grand Canyon, but it's way bigger, okay? Our own Grand Canyon was carved out by erosion. And next class, next Monday, you will see that certainly this was once covered with water and there's all kinds of sand dunes. But it turns out this feature is just too big, too crazy to be strictly erosional. This is a cool combination of erosion, but probably what started it off in the beginning was some kind of plate tectonics. Literally something stressed and fractured the crust of Mars and caused it to semi-collapse. And then water probably slooshed all through it and carved it out. So this is you can actually see all 4 geological processes manifesting themselves and fighting each other on the surface of Mars. Okay, let's not try to solve it all at once, but this is how we're going to, and when we see new planets, when we look at planets outside the asteroid belt, when we look at the moons of Jupiter and Uranus, I want us to start thinking like a planetary scientist. When they see a picture of a new planet or a moon, the first question they ask themselves is, what type of geology is going on here? What's happening to sculpt this planet? Okay. A few words about each of these if I can. Impact cratering. The first thing that I'd like you to think about is Earth versus the moon. They're separated by a mere 400,000 kilometers in space. As you all know from looking at the pictures last week, or actually, sorry, on Monday, we did a lunar features lab, right? The moon is covered with impact craters. How about Earth? Nothing. So am I supposed to believe that all of the asteroids and the meteoroids and the comet fragments and the weirdo rocks flying through space, they all just happened to miss Earth, but hit the moon? Yeah, Jenna.
Is it related to the atmosphere? Because a lot of those debris gets burnt out in Earth's atmosphere, rest of the moon, it just hits it.
That's your first thought, Jenna. But it turns out that's not good enough because the atmosphere will only protect you from meteoroids under a meter in diameter. Remember, a meter is about the diameter of my dry erase board. Earth is, by the way, do you remember the crater Plato from Monday? Let's see how good your memory is. How big was the crater Plato?
Wasn't it roughly around the size of, bigger than the size of Rhode Island?
Right. But if you also remember, Ryan, Plato was pretty similar in size to all those thousands of other craters we saw all over the surface, right? The atmosphere, Jenna, okay, just because the crater is the size of Rhode Island does not mean the meteoroid which struck it was the size of Rhode Island. Let's talk a little bit about how this works. There are meteoroids. Let's have a couple of definitions here. There are meteors and there are meteorites. I want a one-word definition for each of these. The meteoroid is when the rock is in space, traveling at some high velocity with a high kinetic energy. The meteor is when the rock hits the sky and makes a big fireball, or as the Rhode Islanders call them, shooting stars, okay? Shooting stars, that's a meteor, okay? And then when you get to meteorites, that's when the rock makes it to the ground. So for instance, this is an iron meteorite. It's already made its journey through space. Obviously, meteoroids flying through space will not always be spherical, but did I tell you guys the joke about the spherical cow? Or was that the other class? I can't remember. Picture a spherical cow? Oh. Astronomers, physicists, they tend to just pretend everything is a sphere because they know the volume and the surface area of a sphere. So this isn't a sphere, but let's say it's a sphere because who cares, right? Okay, so we have some meteoroid. The meteoroid, usually we measure their diameters. That's how we, and for planets we think about radii, but meteoroids we think of diameter. They're flying through space at an extremely high velocity. If you're being whipped around the sun, velocities somewhere between 10 and 30 kilometers per second are going to be the norm. Anything that travels too much slower than that will spiral into the sun. Anything that travels too much faster than that will fly out of the solar system. A typical meteoroid speed when it strikes Earth could be something like 15 to 20 kilometers per second. I got to say that's wicked fast. That's like 20 to 30,000 miles per hour. Obviously, a massive lump of rock or metal traveling at 30,000 miles per hour is going to have an insane kinetic energy. They're basically going to hit the ground with an energy many, many times over a nuclear explosion. When they hit the ground, that kinetic energy will vaporize and melt rock, and it will create an impact crater. Let's make a little model of an impact crater together so we can have some terms. This part of the crater is called the rim. The bowl that it excavates is called the basin. You guys remember that some of our craters will feature a central peak. And you'll also remember that the material that gets blasted out of it will often be seen splattered around the crater in the form of rays, or sometimes we call it ejecta. A good rule of thumb, and this is how I started this whole thing, is that the crater diameter will usually be a factor of 10 to 100 times greater than the diameter of the meteoroid which strikes it, okay? So a simple rule of thumb is crater diameter is equal to 10 to 100 times the impactor diameter. Sorry, that got kind of squished over to the side there. Now that we know this stuff, let's quickly look at that image of the moon we have again. How easy would it be for me to find that? I could just go to, let's try here. HR Astro Waxing Gibbous. Let's see if we can just, boom. That was probably the fastest way to go about this. Now, this is upside down from, this guy's up here. That was crater Plato, right? So my point, Ryan remembered that it's about the size of Rhode Island. So if Rhode Island is 80 kilometers long, I would say that the rock that hit that thing was probably 8 kilometers in diameter. That's just a quick off-the-cuff guess based on the arguments I made to you. The first point I'm making, Jenna, is many of these objects are comparable in size to Plato. So the moon has been hit with many large impactors. Now, Jenna's first thought of why the Earth doesn't show impact cratering is, well, Earth's got an atmosphere. Doesn't the atmosphere burn up some of these meteoroids in a fireball? Yes, Jenna, it will, under a meter in diameter. But the bad boy that created a 80-kilometer size crater had to at least be 8 kilometers or so. That's 8,000 meters, right? That's well past the point where the atmosphere will burn it up. If you were to ask me a question, how often does Earth get hit? I would say that question doesn't make sense because you have to modify it by how often does Earth get hit by an impactor of size X? And I have a little cartoon graph that shows you the frequency with which Earth is struck by different sorts of meteoroids. Whoa, it's doing the thing where you can't see the mouse. I don't care though. Why can't I see my mouse? Hold on a sec, guys. I think it's because I'm in slideshow mode here. Yep, that's what it was. Okay. Just a second. Just a second. Here we go. Consider slide 109. Every hour of every day, Earth is struck by objects approximately 1 meter or so in diameter or less, and gets even higher in frequency the smaller they get. So little bits of rock are constantly raining down in the atmosphere of Earth. Under a meter, yes, Jenna, the atmosphere will burn them up into dust and smoke. Once they get over a meter or so, this is capable of actually hitting the ground, creating a small impact crater or an atmospheric explosion. By the time you get over 100 meters, these kinds of things happen every million years to every 100 million years. You get something big, something that's like really going to make some noise, create a massive crater, maybe have a little bit of climate change. Maybe a few times in Earth's history, maybe once a billion years or so, you get hit with the big boys, the dinosaur killing meteoroids that impact almost all living organisms on Earth, that can fundamentally change surface geology. I mean, hell, if you just go to the Wikipedia the Wikipedia page on extinction event, you discover that nature is incredibly wasteful in her design of life, extinction event, and that throughout Earth's history, as we study fossil records over the last 500 million years, nature has periodically wiped out huge fractions of all organisms on Earth. The most intense one was at the boundary of the Permian and Triassic period, where some unknown mysterious circumstance suddenly caused maybe, I think it was 80% of land life and 95% of marine life to suddenly perish in a short period of time and go extinct. Literally, all the organisms that came afterwards had to build off of the small number that survived. And you can see that this isn't the only one. At random chaotic intervals, we have these huge spikes in extinction. What could be causing them? This is a subject of some debate. One theory is periodic climate change. Another is this could be every time Earth gets struck with some really big meteoroid. And in fact, the two could actually be connected to each other. If you kick up enough dust into your atmosphere, if you change your global albedo, you can actually change the climate of the planet on a short-term basis. Seeing those spikes in extinction make you realize, wow, Earth has been getting pegged just as often as the moon. If you can see that many craters on the surface of the moon, don't be fooled into thinking that Earth hasn't been struck with just as many of them. So why don't I see them on the surface of Earth then?
Probably a combination of erosion and plate tectonics.
That's the key idea. Other types of active geology erase the craters. Every planet gets hit sooner or later because time is long and there are many rocks whizzing around the solar system. The only planets that don't show evidence of impact cratering are planets that have the other four geological processes working against them to repave the driveway, so to speak. Okay, so let's take a couple of notes on this because this is sort of the important planetary science takeaway about impact cratering. Okay. How should we think about impact cratering? Let's sum it up in a couple of bullet points that will concrete these ideas. The first is that all planets get hit. In the case of impact cratering, size doesn't matter. Sure, it's probably very tempting to think that Earth is a much bigger target than the moon. But 6,000 kilometers versus 2,000 kilometers, this is nothing compared to the giant target that is the solar system itself. These are both small in comparison to space. The only reason these things get hit at all is because they sit in outer space for billions of years, and there are probably, wouldn't even begin to try to estimate the number of rocks flying around the solar system that could be between 1 and 100 meters. Hell, every time we go through the path of a comet, we get periodic meteor showers as we just stream through a bunch of rocky debris. Even though all planets get hit with impact craters, not all planets, or let's put it this way, not all planetary surfaces show, and here's the key word, evidence of cratering. Oops, period. Why? Because of basically what Ian said. Other forms of geology, and Ian mentioned plate tectonics and erosion, but you will see, Ian, when you study the surface of Mars, that volcanism is perfectly capable of just coating the surface of a planet with lava and completely erasing evidence of craters. In fact, I want to show this to you. On Monday's class, we're going to use this Mars topographical map made by they call it the Mars Mola Map, made by the Mola satellite. The Mola is Mars Orbital Laser Altimeter. Basically, a satellite flies around Mars, shines a laser at the surface and bounces it off and makes a very precise topographical map. And then they color code it so you can really see what's going on here. And I want to just tiptoe over to Mars's volcanoes and see what you think about it. This is kind of a high-res image, so give me a second. Let's zoom in to the Tharsis Montes plains. Oh, it's Control Plus. There we go. Let me zoom out. What do you think, Ian?
It looks very smooth compared to what's around it.
Yeah, like here, you can see that at one point there was all of this cratered terrain covering the surface of Mars. And look at what happens to the density of craters as we travel closer and closer to the volcanoes. You can almost see different epochs of eruptions coating the surface. At one point, all of this lower yellow terrain was probably covered with impact craters. Then eruptions created this orange stuff, which has now started to creep in with craters over time. Then there's these red epochs of eruptions, and then eventually the much more modern brown stuff, which sits on top of it. And notice how much smoother the terrain gets as we get closer. Mars doesn't anymore have any active water. It does have wind erosion, so erosion does play a role in this, but you can literally see volcanism repaving and recoating the surface of Mars. If you took away those volcanoes, there would be craters underneath, right?
Out of curiosity, I'm sure that they're not active, but there's no active volcanoes on Mars because it's like frozen over for the most part.
Yeah, and that's what we're going to cover in our next section if we can even get there. But remember that the depth of Mars's lithosphere is roughly half its radius, we suspect. The only way you can have volcanism is if you can create cracks and vents in your lithosphere such that warm material can flow through, build up pressure, and pop and blow like a zit onto the surface, right? But Mars, its lithosphere is too thick to let that happen anymore. Certainly in the past it did. Okay, this leads to an important, just two more little concepts in this. By the way, how am I doing on time? It's 1:25. I knew this always happens to me. Okay, so actually I'm going to erase so I don't have to crouch down. Can I do that? Can I erase this? Okay. Here's what we have just learned. And here's one of the key metrics that planetary scientists use when they study the surfaces of planets. The density of impact craters, and literally we could measure it in something like impacts per square kilometer. The density of impact craters is an indication of the surface age of the planet. And the reason why I underline surface age is I want you guys to remember that all planets are essentially the same age. Like they all have the same birthday, which is 4.6 billion years ago, right? But the surfaces of the planets do not all have the same age. The surface of the moon is way older than the surface of Earth. If you travel around Earth, you are hard-pressed to find any piece of rock that hasn't been totally transformed in the last 300 million years. On the surface of the moon, there are rocks that haven't changed their form or shape in 4.6 billion years. The surface of the moon is way older than the surface of Earth. Yet the moon and the Earth formed together at the same time, right? This is why I'm saying surface age. If you see a high density of impact craters, that's an old surface. If you see a low density or no impact craters, you see a young surface. You know, before the New Horizons mission flew past Pluto, I had no idea what the surface of that planetary world looked like. No one had ever seen a good high-resolution picture because it was too far away. Have you guys seen the picture of Pluto? Do you know what it looks like?
It's gorgeous.
And let's have you test out this theory. It's gorgeous. That's the right way to put it. It's completely majestic. True color right there. What would you say, Ian, Ooh, do I dare do 8,000 pixels? Yeah, baby. Give it to me. Okay. Look at this. What do you think?
It looks like, for the most part, it's probably pretty old.
Where's my razor? Where's my shotgun so I can just go end it all over there off camera? Pretty old? Pretty old? Why?
There's a lot of craters.
Hell, okay, look, man, you ain't been poking around the solar system long enough like an old dog like me. Let's
Oh, wait.
uh,
Oh, I guess we're talking about density, not amount.
well,
Is that what you're saying to me?
Mercury Planet. Here. This is what the surface of Mercury looks like. How about just a moon? Like, I got it. Callisto. Here's a moon of Jupiter. See all those little white spots? Those are impact craters. That's what an old surface looks like, right? I was thinking the opposite. Look how smooth the Regio Tumbi is, the so-called whale's tail. Can you even see a single crater there?
Yeah, I guess that's true. I was kind of looking at that and thinking, oh, that's ice. That doesn't count. I don't know why.
Ice totally fucking counts. You can make a
Yeah.
crater in ice just the same as you can make a crater in rock. In fact, at Pluto's distance from the sun, ice has the hardness of rock. The mountains of Pluto are made out of solid ice, and they would be harder to the touch than granite in Mount Washington because of how cold it is. You want to know what the NASA scientists said when they first downloaded this image and displayed it on the screen? One of the guys jumped up and shouted, "Houston, we have geology." And what that meant was, holy effing shit, there's no impact craters. Do you want to know what we thought the closest thing to Pluto might be before we had this picture? There's a moon of Neptune called Triton. Okay. And Triton also has a relatively smooth surface. There's some crazy ass geology going on here. I'm still not giving you the right. I'm showing you the cool moons. The cool moons are the ones that have smooth surface. I don't know why the internet's mad at me right now, but if you go to any other moon, like even if you were to go to Ganymede, you can see craters all over the surface of this thing, right? And this is basically a big ice ball in space. And you can see, well, all right, Ganymede's not even, I don't know. Anyways, you get the point. Mercury, the moon, those surfaces are covered with impact craters. They're very old. I wanted you to look at Pluto, Ian, and it's okay. It's your first time doing this. So I wanted you to see, oh, wow, it's a really smooth surface. That means Pluto is geologically active somehow. Low density of craters, young surface. Doesn't matter if it's metal, rock, or ice, okay? All right. Okay, it's 1:31. I need to talk about those other forms of geology. Screw it. I think I made the more important point. Density of craters is all planets that are old show impact craters. As they get more geologically active, they cover up the surfaces. On Monday, we'll do the other three. Maybe I'll start to get into the role that atmospheres have to play. Let's take a little kids break before we attempt our homework today, shall we? So maybe 1:45, 1:50, we'll get to it. Does that sound good to everyone? Okay. All right, I'll see you guys then. It's time for homework 9. Let's set her up. We've got a name. We've got astronomy 1010. I'm pretty sure this is homework number 9 today. It should be the problems from actually chapter 9, conveniently. Do you have the numbers in front of you, Ian? Could everyone?
Yeah, it's 48, 55, 57, 59, and 60.
All right. Chapter 9, 48. Ian, take us out.
All right, this is a short answer. It says miniature Mars. Suppose Mars had turned out to be significantly smaller than its current size, say the size of our moon. How would this have affected the number of geological features due to each of the 4 major geological processes? And do you think Mars would be a better or worse candidate for harboring extraterrestrial life?
So our goal in this short answer is to address if Mars were to shrink to the size of the moon, how would it have affected the 4 geological processes, which are clearly evident on Mars? And considering that we are in the process of investigating the permafrost of Mars for potential microorganisms, life, what would the chances of life existing on Mars be like if it had started out smaller and developed to the size of our moon? Based on our discussion today, is the answer to that question obvious, or is that a little confusing? What do you think?
I mean, I can kind of make a guess for life, but how it would affect the 4 geological processes is a bit more of a problem for me.
What if we applied some of the concepts that we learned in our lecture today?
Yeah, I'm trying to think.
Because we actually are pretty well suited at this point to address this question. How about Ryan, Kim, Jenna? You want to join this convo? Tell me what you think.
I mean, it could have something to do, and this is, so I guess one of the main geological processes that are active on Mars are volcanism and impact craters. And we were talking about like the heat of the planet with in terms of like the light, the internal temperature. So I think if it was smaller, it would have less internal temperature, so the volcanism would be less active, right?
Why? Yeah. So can you run me through that logic? Why would there be less volcanism?
Because since it's the watts per meter squared, it would have less surface area, so there'd be less internal temperature.
It's that volume to surface area ratio thing, right?
Yeah.
A smaller Mars would have had what happened to its interior?
Yeah, there would have been less heat inside of it, so it would have frozen over faster. There'd be less volcanic activity.
Yeah. You didn't. It's not your fault really, because we didn't quite get enough to address erosion. When we think of erosion on Earth, we think of water erosion primarily. And glaciation is also a form of erosion. They carve out mountain valleys.
Ah.
A third very important form of erosion, which is active on Mars, is wind erosion. Now, I want you guys to take a look at a picture from, I don't know if this was Curiosity, it must be Curiosity rover. I don't think Perseverance has too many photos out yet. Do you see all those rocks scattered around the surface of Mars there? How would you say they're different than rocks on Earth? Like, look at all those rocks.
They're a lot more jagged. They look like fragile.
Yes. What does that mean to you, Jenna? Why are they so sharp and pointy and flinty like that?
Less erosion, less wind erosion.
Water erosion.
Mhm.
It turns out Mars has an active and robust level of wind erosion. And if we can get any close-up images of these rocks, you'll actually see it in the form of sand blasting. The rocks are all, they have tiny little pits and grooves on them where dust storms, surface Mars, rocks, I don't know. I definitely have some pictures of them somewhere. You can see, oh, this. Oh, that's low resolution. Yes, this is perfect. Do you see those rocks, how they look like cauliflower? That's all sandblasting. That's wind erosion carrying tiny grains of sand and just chipping. We don't see that kind of thing so much on Earth because water is a more potent and powerful form of erosion. In fact, I want to show you guys two pictures of Mars taken with the Hubble Space Telescope roughly a month apart in 2001, function F5-107. In June of 2001, Hubble Space Telescope takes the left image of Mars. Visible in the photograph are the ice caps and many of the large-scale geological features. Do you see this picture from a month later? The entire planet is covered in a global dust storm. The pressure of Mars's atmosphere is much lower than ours. So you can't get blown around by a hurricane on Mars the same way, or I don't think you can. The pressure isn't enough to have a gust of wind blow you over like you can on Earth. But it does carry around fine little grits of sand that can blast away at the surface of rocks. So actually, even though Mars is bone dry and doesn't have any water erosion, and Jenna could see that in the flinty, jagged, pointy rocks, no water to smooth out their surfaces, Mars still does have erosion. So in fact, let's go through this again. Mars shrinks to the size of the moon. What happens to the interior of the planet?
Gets colder.
What happens to the lithosphere of the planet?
It hardens faster.
Gets thicker.
Which geological processes would be immediately affected by this?
Volcanism and plate tectonics.
Erosion.
Mars did have a little bit of plate tectonics in the past. Plate tectonics requires you to have a fractured, cracked lithosphere. You have to have lithospheric plates. And remember, I think I still have it up here, that topographical map. Can you guys see how those three volcanoes are in a row? That suggests like plates moving over a convective hotspot. And as I mentioned earlier, the Valles Marineris, I once showed this picture of Mars to one of my geology colleagues, and she said the coolest thing. She's like, look at all that red overlying rock. It's as if the underlying convection in the mantle is just pushing up and pushing up and pushing up at the same spot on Mars. Without a robust set of plate tectonics, the plates aren't lifting over it. So it's just stress, stress, stress as convection pushes up on it. It probably caused part of Mars's lithosphere to rupture and fracture into this crack. On the other hand, one thing that you guys may not realize about planets yet is planets don't start with atmospheres. They form their atmospheres over time through, wait for it, volcanism. And if erosion takes the form of wind, water, and ice, without an atmosphere, you don't get wind. Without an atmosphere, you don't have water because you need pressure to have a liquid. And without an atmosphere to like have some climate stability, your ice isn't going to really drift around like in glaciation. It might just, well, actually the ice caps of Mars do come and go. So you could still have a bit of ice without an atmosphere, but wind and water are immediately at the table. Let's put all this into a big thought bubble, okay? If Mars had formed smaller, say the size of our moon, we would expect to see much less of the interesting geological features that cover its surface today. Let's elaborate on this and really get into it. A smaller Mars would cool much faster, resulting in a thick do I want to say impenetrable? Fine. Impenetrable lithosphere. I think there's probably a better word, but my mushy mind, this is the best I can do right now, okay?
It works.
Yep, a thick impenetrable lithosphere. A thick lithosphere would be unable to form vents or fractures necessary for volcanism or plate tectonics. All right, I'm going to have to continue back up here. So let's let you guys catch up while I get some water here, or some coffee, rather. I think I'm going to kind of erase the top part of this. Okay, continuing on. Gone. Let's try this again. The tall volcanoes of the Tharsis Montes plains would never have formed. I think it's Tharsis Montes. Let's see if I got that right. It's kind of cool if you can use the proper name, the Tharsis Montes region. That's what I'm referring to there, those three volcanoes. The tall volcanoes of the Tharsis Montes plains, sorry about my handwriting today, would never have formed, nor would the epic Valles Marineris form from a ruptured lithosphere. Without volcanoes, Mars could not have formed its thin atmosphere, which means, can I erase the bottom stuff? You guys catching up with me here? You cool? Ryan, Kim, are you guys okay? Speak now. Kim, you cool? All right. Without volcanoes, Mars could not have formed its thin atmosphere, which means which means, let's face it, no wind erosion and none of the dried riverbeds would exist. We've covered 3 of our 4 geological processes. Which one have we not touched on?
Impact craters, which
So what would happen to the impact cratering?
I think it would pretty much stay the same, right? Well, maybe even get more of them because there's no atmosphere.
This is a
to break the
semantic
small ones.
argument. I don't think Mars would have been hit by a different number of meteoroids throughout its career, but the evidence of impact cratering would go way up, right? Because there wouldn't have been any other geology to erase them. Impact craters would dominate the surface as they do the southern hemisphere. So here we're referencing a couple of things that you might not have noticed with our very brief picture here. The southern hemisphere of Mars is very heavily cratered, and most of that cratering is probably left over from the heavy bombardment period. I haven't really got to talk to you about that yet. I do want to point out to you, to see this, look at those, those basically are a dead spitting image of rivers on Earth. None of that cool stuff would be there unless Mars had had a very wet period with a lot of liquid water. No atmosphere, no volcanoes, no water. In fact, this was probably a giant ocean. Mars's entire northern hemisphere was probably, look, you can see the rivers flowing out into the Crisi Planitia like tributaries flowing into a massive ocean. All that would be gone. What you would get instead is basically this. This is what the entire surface of the planet would look like, right? One last sentence. In short, a miniature Mars would resemble the moon. If you shrink something to the size of the moon, you get the moon, right? Would resemble the moon. And let's sum up the moon in a sentence. An airless, cratered rock. An airless, cratered rock incapable of supporting life. For this reason, scientists believe that one of the key properties that determines the overall evolution of a planet is its size. If you want to look for life outside of our solar system, you better find a big Earth-sized planet. You're not going to find it on a Mercury or a moon-sized object. That's the rough idea. Kim, are you still writing? You're good? Okay, all right. I'm erasing. Ryan, you want to read us one? Or actually, let's go in order here so I don't get confused. Oh, Jenna, yeah? Kim, I'm gonna cycle around this way. Kim, you read us our next problem if you're willing. It's
Okay.
chapter.
Yep. It is surface to volume ratio. Compare the surface area to volume ratios of A, the moon and Mars, B, Earth and Venus, and in each case, use your answer to discuss the differences in the internal heat of the two worlds.
In the book, they presented the cooling rate of the planet in terms of the surface area to volume ratio. That's how it's typically done in a graduate book. The problem is that the surface area to volume ratio is proportional to the inverse of the radius, 1 over r. I know that my students don't like things in the denominator. It just messes you guys up. So rather than discuss a planet in terms of its cooling rate, I prefer to flip it and reverse it and think about the planet in terms of its heat holding capacity. It seems about the same to me. The volume to surface area ratio is proportional to the radius of a planet. And it's sort of an indicator of the amount of heat holding capacity of a planet. Therefore, if in part A was Moon versus Mars, was that correct, Kim?
Hang on, I gotta switch over the screen. Part A was the moon and Mars, yes.
Okay. Mars versus the moon. The radius of Mars from our earlier lecture, 3,400 kilometers. The radius of the moon, 1,700 kilometers. Therefore, if I compare their volume to surface area ratios, so we'll do the volume to surface area ratio of Mars over the volume to surface area ratio of the moon. Remember, that's equal to 1/3 the radius of Mars over 1/3 the radius of the moon. The 1/3s don't matter. They're just a static factor. They cancel out. What it really is about the ratio of their radii. 3,400 kilometers to 1,700 kilometers. And what do you get if you divide those things? Loosey-goosey speaking.
About 2.
Roughly 2. And what's the meaning of the 2? Jenna.
Mars is 2 times greater than the moon.
Well, right, but it's not just about the radius. It's about,
Oh, it heats up 2 times faster.
don't say heats up. Mars isn't cooking on the oven here. It holds twice as much internal heat, right? All right, something like that. Mars holds roughly 2 times more internal heat than the moon. Now in part B, we're going to do Earth versus Venus. Here we'll get right the hell into it. The volume, how do I want to write this here? The volume to surface area ratio of Earth over the volume to surface area ratio of Venus will go as the radius of Earth over the radius of Venus, 6,400 kilometers over 6,100 kilometers. And that is roughly take it away, you guys.
It's about 1. It's
what
like
does that mean?
1.05 since we need to see it.
Or forget about the 0.05s. What's the 1 mean?
It's about the same.
What's about the same? Say it.
heat holding capacity of Earth and Venus are relatively the same.
Good. Earth and Venus hold similar amounts of heat. I wanted to say internal heat, but I ran out of chalkboard space. Two down, three to go. Ryan, could I get your help reading number 57?
Yeah, might I just finish writing this one answer down?
Good, yes. Let me know when you're done, I'll race.
All right.
All right,
It's number 57, right?
yes, please.
Lunar footprints. Assume that the moon is hit by about 25 million micrometeorites impacts each day. This number comes from observations of meteors in Earth's atmosphere, and that these impacts strike randomly around the moon's surface. Also assume that it takes about 20 such impacts to destroy a footprint. About how long would it take for one of these footprints left by the Apollo astronauts to be erased? Hence, use the moon's surface area to determine the impact rate per square centimeter and estimate the size of a footprint.
We're going to do it in a slightly different way. Let's draw the moon with its radius of 1,700 kilometers. And somewhere on the moon, Neil Armstrong left a boot print in the lunar regolith. Now, you guys may not realize this, but this problem is actually based on a legendarily famous photo from boot print in the moon. Do you know when the Apollo astronauts got to the moon, the first thing that they were shocked to discover is the entire surface of the moon was ground up into a 3 to 4 centimeter deep layer of powdery soil. I'm talking moon dust. The entire surface of the moon is covered in moon dust. So much so that when they walked around in it, oh wow, look at that high resolution picture. They left boot prints. This is known as the lunar regolith. In the lunar regolith, they realized that what made the moon's surface so powdery was because the moon has absolutely no atmosphere. It touches the vacuum of space. Every little pea-sized grain of sand that strikes the moon makes a little impact crater, and over billions of years, all those little bombardments of micrometeorites have ground up the surface of the moon into dust, into moon dust. In fact, it was a bit of a problem, I guess, when they would go back into the landing module to try to eat dinner or something. They were dragging huge amounts of ground up silica dust, and they were like inhaling silicate particles, and they actually started to worry that they were going to suffocate and die up there because it was so powdery particulate, and it's mostly just ground up grains of sand, right? Now, think about this. If I were to step outside into a backyard somewhere in Smithfield or something, and I put my boot print into some mucky, gooey, oozy black earth, that boot print would get washed away in a matter of days. It would get covered up by leaves and twigs. One rainstorm and it would be gone. But imagine this boot print sitting there to this day on the surface of the moon. Never a gust of wind, never a drop of rain, nothing but the vacuum of space perfectly preserving this footprint. The only type of geology that could erase this footprint is continuously more bombardment by micrometeorites from space. In this problem, we'll try to estimate how long that boot print will sit there. Let's imagine we're running this problem using what physicists call the Monte Carlo method, after the famous gambling resort. Imagine that I had a computerized robot that could throw darts at the moon, 25 million darts per day. And each dart has to strike the moon, but the location at which it strikes is completely random. You never know where the next dot will land. Our first goal is going to be to try to calculate the probability of a single micrometeorite, a single dart, hitting the boot print. How could I do such a thing? Let's start with a cartoon analogy. What if Neil Armstrong's boot was so big that it covered 1/4 of the moon's surface area? What would the probability be that one of my micrometeorites would strike the boot?
It would be a quarter, right?
And how do you know that?
Because if it's a quarter of the surface area, then that's the likelihood.
So in other words, you're saying that the probability should go as the area of the boot divided by the area of the moon, right?
Yes.
Because if it was 1/10, you'd expect 1 out of every 10 darts to hit it.
Yes.
Obviously, the ratios are way more lopsided, but the concept is still the same. The probability of a single dart hitting the boot print is the area of the boot divided by the area of the moon. Now, the area of the moon is simple because the moon is a sphere, and the surface area of a sphere is 4 pi radius of the moon squared. What should we do for the area of a boot print? Ooh, I've got the perfect astronaut boot. Sit tight. Well, kind of, yeah, it's for cold weather. When I'm out at the observatory, standing on concrete for hours in sub-zero temperatures, I like to have, I should get a product placement endorsement. I got these Muck Boot Arctic Pros. They have like 8 layers of neoprene in them. They're rated down to like -60 degrees Fahrenheit. You know how I knew this was the right boot for me? I read the Amazon testimonials from Wisconsin farmers. And they were like, if I'm going to be out in the barn all day pitching hay, this is the only boot that'll keep my toes warm. So I was like, all right, this is what I need for observing. It's so thick and chunky that it's probably comparable to the bloody astronaut boots. All right, they're probably about this size. Let's model the boot, you know, picture a spherical cow. Let's model our boot as a rough rectangle. The rectangle is maybe 30 centimeters long, right? And maybe 10 or so centimeters wide. That's close to what the area of a boot print would be. So at the top, we'll do 30 centimeters. We're basically making it a rectangle, right? Let me change to black here. (30 by 10 centimeters). Ian, I don't want to go plugging in the radius of the moon as 1,700 kilometers, do I?
No, you would want to put it into centimeters.
Do you know the quick and dirty way to do that?
It's
I'm not remembering it off the top of my head,
Jenna
but
does. I heard Jenna start to say it. Jenna, school.
10 to the 5th
10 to the 5th what?
centimeters
Per.
per 1 kilometer.
Good. That will help you. So what will the final radius be then in centimeters? Sorry, I got to turn the heat down, guys. I'm starting to boil. Why don't I turn this heat down? Sorry, what'd you get?
17 times 10 to the 7th, I believe.
Fine.
Or 1.7 times 10 to the 8th.
Or 1.7 billion? I don't know.
Billion is 9. You're not at 1.7 billion. Right? It's 1.700 million or 170 million centimeters, whatever. Okay, so let's work out the probability then. It's 300 centimeters squared divided by 4 divided by pi divided by 1.7 times 10 to the 8 centimeters squared. Punching that in is a U job. Don't forget your square. I had never seen that boot print picture so high resolution before. It's so wild. It almost looks like it's in modeling clay. Can you see that? I've seen this picture many, many times before, but I'd never seen it with so much resolution. That's pretty cool.
I got 2 times 10 to the negative 14th. And that would be the...
Did you square your radius?
I guess I hit square at the end. Maybe I should have done that separately.
Oh, sorry. What'd you get?
2 times 10 to the negative 14th.
Yeah, no, that's not right. You got to square, then hit equals, right? You don't want to square the whole thing.
Yeah, okay. I did that wrong. Okay.
I know Kim and Ryan and Jenna are busy punching it too, right? We don't need no slackers on our astronaut team.
So would it be
Did I? I'm still
8?
recording. Okay.
8 times 10 to the negative 16th?
Fine.
Okay.
What are the units?
Well, it's a probability, so
No units?
Say that, Jenna?
Is it no units?
Right, there's no units. If your probability is 0.25, that means a 25% chance of happening.
Yeah.
What does it mean if your probability is 8 times 10 to the negative 16?
A very small chance.
A wicked small chance that even one dart will hit the damn boot. On the other hand, we are hitting the moon with a lot of micrometeorites per day, 25 million. You know, the hard thing about probabilities in a way is now that you've gotten good at dimensional analysis, without some units to cancel out, you start to realize it's kind of hard to think. Even though a probability is unitless, it doesn't mean that we can't be clever and assign units to it if we do it in a logical way. The ratio of the boot area to the moon area is like the ratio of the number of times you'll have a boot strike or a boot impact versus a moon impact, right? So we could imagine that we're dividing impacts by impacts. In other words, these units should cancel and be unitless, but the difference is the top is a foot impact, whereas the bottom is a moon impact. So these are dummy units. They're really unitless, but 8 times 10 to the minus 16 means foot impacts per moon impact. Let's go back up here to our 25 million. Are these foot imps or are these moon imps?
They're moon impacts.
Right. So this is 25 million moon impacts per day. To destroy the foot, are these foot impacts or moon impacts?
Foot.
Let's use these modifiers in dimensional analysis to figure out how long it'll take for 20 impacts to hit the foot. Right now we have foot impacts per moon impact. We also know how many moon impacts strike per day, but I don't want to know how many moon impacts strike per day. I want to know how many foot strikes I get per day. How could I calculate the number of foot strikes per day?
You would divide that, right? So the 20 over the 25 million.
Forget about, that would give you per days.
Yeah. Okay.
Do we just replace the 20 with the? Oh wait, never mind. I got confused.
Let me try to say that one more time. Listen to me carefully. You know how many impacts strike the entire moon in a day. I would like to know how many impacts strike the foot an entire day.
Would we use the probability and multiply that by the impacts per day of the whole moon?
That's right. Moon impacts per day on bottom would cancel moon impacts per day on top. Our leftover units would be foot impacts per day. That seems useful to me. Let's do that. 25 million. Sorry. Yeah. 25 million moon imps per day times a probability of 8 times 10 to the minus 16 foot imps per moon imp give us what?
Bless you.
Must be all that moon dust. Yeah.
2 times 10 to the negative, or 2 times 10 to the negative 8th.
Units?
Foot impacts
Almost.
per day.
Thank you. Moon imps cancel with moon imps. 2 times 10 to the minus 8 foot imps per day. Jenna, what does it mean if I have 10 to the minus 8 foot impacts per day? Or anyone whose name is not Jenna but would like to contribute.
It's kind of just an averaged, like very, very small fraction to represent that it does not happen often at all.
Yeah.
Yeah,
that's what I
yeah.
was-
Hold on. I mean, how can a foot be hit by a fraction of a hit? Either you're hit or you're not hit, right?
Yeah,
Or-
so I guess I didn't say it well because it's not necessarily going to happen every single day,
Good.
but it's representing that, like, if you were to average it out to like every day there's a hit, then it's
That is beautiful, Ian. In fact, Ian, the more you put it like that, it's not going to hit every day because it's a probability of, or it's a rate. This is a rate of less
Yeah.
than 1. Rather than knowing the fraction of a foot impact I get per day, don't you think it would be way more useful to know how many days until you got 1 foot impact?
Yes.
How could I get that from this number? How could I take this number of foot impacts per day and find out how many days until the foot gets struck once?
I'm not sure that this is right, but Could it be something to do with the exponent, like how many zeros there are?
In a way, but you're still thinking like a little kid. You're thinking like a little kid who all they can do is look at numbers and they don't pay any attention to units. The units tell you the story. That's how a pro thinks. Instead of looking at your stupid power of -8, why don't you start looking at your units and think about what you're trying to do? I don't want the number of foot impacts per day. I want the number of days per foot impact. You see what I'm saying?
We should flip it, somehow put days on top.
Yeah, what do you call that when you flip a thing upside down? You
Inverse.
the reciprocal. Fine, the inverse. You take the reciprocal, and that will flip the units. Let's do that. In fact, you don't even have to do anything because remember, you have a reciprocal key right there. Just hit Shift 1/X and you're done. So days, write it down like this. Days for 1 foot impact, we would do, I'm going to get rid of this. We would do 1 day divided by 2 times 10 to the -8 foot impacts. What's that get us?
When I hit the 1/X button, it gave me 50 million, so 5 times 10 to the 7th.
I like 50 million. 50 times 10 to the 6 days per foot impact. 1 foot impact is not enough to destroy the foot. 1 little grain won't grind the foot into dust. But the book implies that 20 grains could. So how long do we have?
50 million days, or I guess that times 20, so that would be
Times 20.
100 million.
Yeah, that's a nice round number. You'd have,
or wouldn't it be 1 billion?
huh?
Would it be 1 billion if you're multiplying it by 20?
5 times 2 is 10. Oh, you might be right. Wow. This just shows you how bad my brain is right now. He's right. It's 1 billion days, Jenna, right? Jenna, you said it so confidently, I believed you. You bamboozled me. Thank God Ian caught us. That's why we have to do this as a group, right? 1 billion days. How many years is that? What's the conversion? I'm not doing it.
That it's 27 times 10 to the 6th years.
Like 3
Or approximately,
3 billion.
no.
I mean, sorry, million.
Say
3
it right. I turned 27 to 30, Ryan, because I'm crazy like that.
Okay. 30 times 10 to the 6th years.
Or 30.
30 million?
30
No, I'm sorry.
million.
All right.
That's 10 to the 6 is million.
Okay.
Neil Armstrong's boot print will be stuck on the surface of the lunar regolith for the next 30 million years. I don't even, how old are human beings? Like, how long have Homo sapiens existed?
200,000 years.
Think about that, Ian. That boot print will be there long after we've evolved into hyper-intelligent dragonflies or cyborg monsters or something. Like, that boot print will outlive Homo sapiens as a species. We couldn't even stay the same if we tried. That's wild.
Definitely.
Cool beans. I love this problem. Gets you thinking about things. Okay. You guys got it all down? Did you box it? Let's erase it and move on. We're cruising. Jenna, can you hook us up with some 59?
Okay, 59 is internal versus external heating. In daylight, Earth's surface absorbs about 400 watts per square meter. Earth's internal radioactivity produces a total of 30 trillion watts that leak out through our planet's entire surface.
Jenna, before you go on, this is actually a really cool problem. Let's draw a little picture together, everyone, okay? Draw a circle to represent Earth. Do you guys remember how I told you that surface temperature is not the same as internal temperature? That's sort of what this problem is about. Here's Earth and its radius. And I'm going to represent the radioactive decay the same way the book did by imagining all of these radioactive nuclei spread throughout the body of the planet, randomly popping and undergoing what we call beta decay. The nuclei spontaneously split apart. And that means flowing out to the surface, the energy that they generate is 30. How many zeros are in a trillion again?
12.
That's right. 30 times 10 to the 12 watts. That's the overall power or the luminosity generated by radioactive decay. And all that's got to flow out to the top. Meanwhile, the sun is beating down on Earth from outer space. So here come some rays of sunlight penetrating through our atmosphere. And if we ask per square meter, what was that number again, Jenna?
400 watts.
But that's not 400 watts over the whole surface of the planet.
Earth's surface absorbs about 400 watts per square meter.
The per square meter matters, Jenna. 400 watts per meter squared. That's like the brightness of the sun beating down per square meter panel. Now continue on with the reading of the problem.
Okay. Calculate the amount of heat from radioactivity decay that flows outward through each square meter of Earth's surface. Your answer should have units of watts per square meter. And then compare quantitatively to solar heating and comment on why internal heating drives geological activity.
Okay. When they say watts per meter squared, that's what we've called the brightness. It's the flow of watts per square meter across a surface. According to the inverse square law, the brightness is the luminosity or power divided by 4 pi r squared. Except here we're watching the radioactive energy leak out the top. The radius of Earth is 6,400 kilometers. How many meters is that? Obviously, you can't get it in watts per meter squared unless you convert to meters, right?
It's 1,000 meters per kilometer.
Okay, so give me the final answer in meters.
It is 6.4 times 10 to the 6th.
Let's calculate the brightness due to radioactivity. 30 trillion watts over 4 pi times 6.4 million meters squared. 2 sig figs is what we want.
Oh, wait, I'm so sorry. Could you just speak so that way we can see the speaker mode? I think it's just like a little box right now.
That's up to you. I am in speaker mode. You need to go to the top right corner, click view, click speaker view, and then double click my little face. Did that fix it, Jenna? All right. I'm ready when you guys are for an answer.
I got 0.06.
I want some units.
That would be meters squared.
No,
Watts per meter squared, sorry.
watts per meter squared. How does that compare to the amount of energy hitting the surface from the sun?
It's minuscule.
Yeah. 400 watts per meter squared over 0.06 watts per meter squared. This, I got to tell you guys, the first time I ever did this problem was when I was teaching this class. And it blew my mind. 6,700 times more energy from sunlight. But this raises a question. There's another part to this question, isn't there, Jenna?
Yep. So it says compare quantitatively to solar heating and comment on why internal heat drives geological activity.
Hey, Ian, I got a thought question for you.
Yeah.
What drives volcanism and plate tectonics?
Internal heat from the planet when the surface cracks.
Right, Ian. And yet we just calculated that the internal heat flowing across our lithosphere is 7,000 times less than sunlight. Why doesn't sunlight drive volcanism, plate tectonics? Doesn't that seem weird to you? That sunlight is 7,000 times more energetic? Why isn't sunlight triggering Mount Vesuvius or Mount St. Helens to erupt?
I want to say it's because one is coming from directly inside the planet and the other one's traveling across a vast distance.
Well, it doesn't matter what the hell happened before. When it strikes down at the surface, we know that we're getting 400 watts per square meter. We can measure that. It doesn't matter if it came from Godzilla's laser eyes or whatever, you know? The energy, if you're into that kind of thing, you know? I guess, yeah, something about it flowing from the inside to the outside that must make the difference, right?
Yeah.
I mean, what happens when the sun hits the surface of Earth anyways? It kind of like heats up the surface. Hell, if you dig a hole much more than a meter or two into the ground, you start to get to some cold Earth, right? Eventually it gets warm again, but at first it gets colder. I don't think sunlight can penetrate down more than a meter in terms of its warming effect of the Earth. Most of that sunlight gets re-radiated and bounces right back off into space. It turns out that although internal heat is way wimpier than sunlight, that internal heat has to flow thermodynamics-wise across the lithosphere barrier through conduction. And it's that weak trickle of energy flowing from inside the planet to the outside, that's what's driving the geology. This question illuminates why surface temperature and internal heat are not the same thing. The surface temperature of a planet is dominated by sunlight. But to actually get some energy flowing across the lithosphere, you've got to come, as you said, Ian, in a way from the inside to the outside. Let's put that into a sentence.
So it's kind of conduction versus radiation.
That's one thing, but you know how I really look at it? I look at it as an issue of entropy and the second law of thermodynamics. Energy is always trying to spread itself out towards maximum disorder. It would be weird if the sunlight heated the Earth and it all just started getting bunched up and concentrated inside the planet. That's how physics doesn't like to do things that way. It wants ice cubes to melt into water. It wants molecules to spread across a room. Energy wants to spread itself out and dissipate, leave from the interior of Earth where it's bunched up and flow across the surface. I need to erase this to write my final sentence, okay? While sunlight provides more energy and heats the surface of a planet, all of this energy is re-radiated back into space. Geothermal energy, conversely, flows across the lithosphere via conduction and drives geological activity. I tried to say that as briefly as possible. Interesting problem, though. Ian, we're back to you. You'll take us home for a final brief problem. Once you're done writing here.
It's 60. Yeah, I'm done.
Hey, Kim, Ryan, do you need another second here, or
Yeah, I do. I'm just about to finish.
just shout at me when you're done, Ryan?
All right, I'm good.
Okay, number 60, Ian.
All right. 60 is plate tectonics. Typical motion of one plate relative to another is 1 centimeter per year. At this rate, how long would it take for two continents 3,000 kilometers apart to collide? What are the global consequences of motion like this?
Okay, let's see if we can draw a couple of continents. Famously, you can notice the jigsaw puzzle nature of South America connecting to the continent of Africa. At one point, these were connected in some kind of a global Pangea continent. You've heard of the Pangea thing before, right?
Yeah.
And plate tectonics through seafloor spreading has been pushing these things apart for a long time, a time which we're about to calculate. So let me see how my art skills here. So I'm going to draw South America. clearly, art was not my forte. Okay, there's South America. Now let's draw the African continent. And these continents have been drifting apart. They're today roughly 3,000 kilometers apart. I think this is what they had in mind for the two continents, personally. The velocity at 1 centimeter per year, that's approximately the rate at which fingernails grow. That's how slowly these continents move. Our goal is to calculate how long, which of course means a time. How should I do that?
Well, first of all, we should probably convert 3,000 kilometers to centimeters.
Great idea. How could we do that super fast?
So that is 1,000,000 centimeters, or 1 times 10 to the 5th, right? We said that was what it was, 10 to the 5th?
10 to the 5th centimeters per kilometer.
Yes.
So let's write that over here. So what does that give me for a separation distance? Oh, Jesus Christ, guys. 5 plus
Isn't
8.
it 3 times 10 to the 8th?
Yeah. Centimeters. Which, if you think about it, Ryan, is also the same as 300 times 10 to the 6 centimeters, correct?
Yes, I believe so.
I kind of like this version better than that version.
Okay.
So now what?
You would try to. I know this. I don't know why I'm blanking right now. Well, you would multiply, right? Or I guess you would do another, the second form of.
Dimensional analysis.
Yeah, thank you. I don't know why I always forget the name.
Now you're talking. Now you're talking. Okay, so Ian, then do that.
Yeah, so that would be the 1 centimeter per year on one side, and then the 3,000 or 300 times 10 to the 6 centimeters on the other side.
I see 4 sides. I don't know what sides you're talking about.
Okay. You would put, I guess, since you want it to cancel out, you would put 1 year on top left, and then 1 centimeter on the bottom.
1 centimeter per year is also 1 year per centimeter, correct?
Yep. And then on the other side, you would just do 300 times 10 to the 6th centimeters on top.
What you're really doing is a version of distance equals rate times time. Distance divided by rate gives you time, but whatever. There's a lot of different ways. I like the way that you gravitated towards the Ian. You said, fuck it, let's just do the dimensional analysis. That's the right way to think, okay? So what do we got then?
300 times 10 to the 6th years. So 300 million years.
What's the answer to the last question? What was that final question that they asked?
Final thing they ask is, what are the global consequences of motion like this?
Okay. So from a planetary science perspective, what does this number mean?
I guess if you're thinking conceptually, it means that the spread and change of continents is very slow.
Well, slow for you.
Yeah.
Fast for the Earth. I don't know.
Okay. Yeah. Not sure what you're looking for.
This question is intentionally vague. It's trying to see if you can draw the big conclusions. 300 million years. What does that mean?
Is that like compared to 4.6 billion? So every third, it's like a 13th of it. Hold on.
Compare this to the problem we did a moment ago with the boot print. Neil Armstrong's boot print will sit at the surface of the moon for 30 million years before meteorites grind it into dust.
So for 13 million years, every 13 million years, a Pangea situation happens.
Not 13, 300 million. Good,
Okay.
now you're getting better. 300 million years is the time to go from Pangea to the current continental arrangement, right? What if we were to leap forward 300 million years? I've got a question for you, Jenna. At the start of today's lecture, I showed Ian, where is it? At the start of today's lecture, I showed Ian this picture, and he immediately went, that's Earth. If I had a snapshot of the Earth 300 million years from now, do you think he would have gotten that question right?
No,
He
it
wouldn't
would all
even
be broken.
recognized his own planet.
Hmm.
From a planetary science perspective, 300 million years is a time scale over which Earth, will molt its skin and just remix up the whole damn thing, not even look like the same planet anymore. This concept is what we mean by a geological time scale. It's a time scale over which things change and become interesting. There are all kinds of different time scales in life. There's an astronomical time scale. Galaxies evolve over billions of years. Stars evolve sort of over billions of years. Planetary surfaces molt over hundreds of millions of years. Interesting things happen in your life over the course of a year. The time scale over which you get bored is probably about 5 minutes, right? Okay, so there are all these different time scales, but this is a geological time scale. Let's write that down. This defines a geological time scale over which plate tectonics will reshape the surface of Earth. And for this reason, it's almost impossible to find any portion of the Earth's crust which is much older than 300 million years. In fact, do you want to know where the oldest chunk of crust on Earth resides? Right here, right where you are. The continental crust of New England, Rhode Island, Massachusetts, upstate New York. This is some of the oldest granite on the planet. It's been smushed up there it's been sitting around there for hundreds of millions of years. Thank God there's something in Rhode Island that's older than me, okay? It's the continental crust under my feet. If you were to go somewhere like the San Andreas Fault or an African Rift Valley, the Himalayan mountains, those changed quite dramatically over the last few years, due to plate tectonics and volcanism. Indonesia, they got a volcano going off every day in Indonesia, right? Okay, well, you've done it. You've completed another homework with me. You've learned about the geology of our planets, and you'll learn a bit more and some stuff on atmospheres next week, okay? Please turn it into homework 9. How many more? I heard you guys talking when I walked away for a sec. How many more weeks do we have?
On your syllabus, we have our final exam on May 5th, rather.
Yeah.
So like 3 weeks.
3 weeks. You know, something I'd be open to, if y'all felt like cutting some corners here, I would be open to skipping the final and letting you double your midterm grade if you feel that you're happy with the way things have been going. So it could be a way for us to parachute out of a whole bunch of stress and free up a day for us to finish up our other classes and things. Do people like that idea or do they not like that idea?
I mean, I can't speak for everyone, but I would totally be down with that.
Yeah?
Yeah, I did okay on the midterm, so I'm down with doubling it.
I agree with Ian too.
Sure. I was figuring most of you would feel that way. I would like that too. Ryan's down as well. I can't decide if I want to. Oh, Naomi's finally we hear from Naomi. I'm here for you, baby. I'm right there in the background. Okay, Naomi. All right. Yes. I figured that this would be potentially an exciting prospect for you guys. However, I want to get this out during the recording. If there are folks out there that really would like to take the final for some reason, I'd like to hear from you so that I can get a sense of who's down. See, for me, I'm looking at about 2 days worth of work to get I have all the exam is done. Ironically, what's so irritating is, you know how awful Blackboard is? Loading each question sometimes takes 5 or 10 minutes because you have to load it and then it gags and it chokes and then you got to load it again and again and again and then it glitches and then you got to load it again. So I've got to do that 100 times and it's just awful. It's just so awful. I would love to weasel out of that work. I mean, I really should get it in there at some point. I did it with the midterm. Now it's done and I'm fine. The point of this class is to realize that planets are cool and science is cool. And I think you've already done that because you've been here listening to me and hanging out with me. And you've already suffered through a midterm exam at which I got to gauge your ability or something. And plus, if you just kind of do the labs and the homeworks, it's all going to work out anyways. So if I can avoid stressing you the F out for a whole bunch of hours at the end of a semester, then that seems like a good thing to me, you know? So anyone out there who actually gets this far in the video, if you are thinking of, I'm assuming that most people don't want to take the final and would rather double their midterm grade. But if you're someone who would like to take the final, I want to hear from you so that I know there's interest out there. That'll help me determine how enthusiastically I have to plug these questions in. Okay. All right, so that's something we should have a discussion about closer toward the end of the class, but we got a couple weeks left, all right? All right, guys, I'll see you on Monday. Over and out.